Good day to all. So, welcome to lecture second of this course on computer organization and architecture. The main contents of this lecture will be we will first briefly discuss, we will first recap what we have done in lecture number 1. Then we will discuss the working of a computer. What is a computer and its working? And after that, we will understand some models, working models or architectures of computer systems and how they differ from each other. From this, we move to the assembly language. Okay, and briefly discuss the structure of a memory in a computer system. Okay, so this lecture we will divide the video into two parts. So the first part is lecture 2A, so in which we will recap the previous lecture, working model of a computer and some models, architectural models for computers. So let's start this lecture. So first of all, let me recap about the definition of computer organization and architecture. So here we have three terms: computer, organization and architecture. Let's first focus on these two terms, organization and architecture. What do we mean by organization and architecture? So as we have discussed in the previous lecture also, the science or art of designing, selecting and interconnecting hardware components. Okay, and designing hardware software interface. So this is the complete definition of computer organization and architecture. Science or art of designing, selecting and interconnecting hardware components and designing hardware software interface. So this part the science or art of designing, selecting and interconnecting hardware components, this is called the organization. And design hardware software interface, this is called the architecture. Or in other words, we say architecture is the instruction set architecture of a computer system. And organization, we also say it micro architecture. Okay, so the first of all, we have to design this interface, design the ISA. The ISA specifies the functionality of our hardware, how our hardware should work, what are the various assumptions that we have to make. Everything is defined in the ISA. After defining the ISA of a computer system, we then implement this ISA. Okay, implement, and the implementation of a particular ISA is called the micro architecture. Okay. One thing you have to note down is that for one ISA, there may be multiple micro architectures. We have already discussed this in the previous lectures, why there is the possibility of multiple micro architectures for a single ISA. Okay, so between the hardware and the software, the interface that allows this software to run on this hardware, this interface is called the instruction set architecture. Okay, so we can say architecture is the view of a computer as presented to software designers. So software designer is here, okay, and hardware is here. The software designer has to run its program on the software. So to present the soft view of a hardware to a software, that particular view is presented with the help of an ISA. So instruction set architecture is the view of this hardware, how this hardware is working to the software. And the organization, as I said, is the actual implementation of a computer in hardware. Okay, so we are fine with these two terms now, organization and architecture. I hope everyone understood these two terms. Now remains the computer part. So what is a computer? Any device, any general purpose device which we can program, and based on this program, this device processes some data and gives us the results. The device is called a computer. So a computer is a general purpose device that can be programmed to process information and yield meaningful results. And how this computer system works, how our computer system works. So let's say this is my computer, or we can also say a CPU, Central Processing Unit, a computer. So this computer takes input. Two things are provided input to the computer. One is a program. What is a program? Program is a set of instructions. And the second thing that is provided as input to the CPU is the data. Data may be images, files, videos, or anything. So CPU takes the instructions, applies these instructions on the data, and gives us the results. So this is the actual working of a computer system. Okay. So here you can see that there are three main components in a computer system. One is computation engine. So computation is done with the help of CPU. The second thing is the storage, or we can say memory. Okay, and this memory is required to store the program and data. And the third part is the communication. Because to take the data or to take the instructions from the memory, we have to connect these components using some wires, and these components have to communicate with each other. So communication is also one key component. Okay, so here you can see that whenever we are writing a program, okay, we have a program, we write the program in a higher level language. We first convert this program into machine specific instructions. And what are the machine specific instructions? The machine specific instruction is the instruction set of a machine. Okay, converting program into machine specific instructions and then running these instructions one by one on the data, and the CPU gives us the results. Okay, so here you can see that we require memory to store this program and data, to store the instructions and the data. The instruction has to be applied on a data, and after applying the instruction on the data, we say that instruction has been executed. After execution of an instruction, we get the output. So for storing these instructions and data, we require a memory. And there are two ways by which we can store the program and data. One is to use a unified memory, And another model is to use separate memory. What I mean by unified memory means that a single memory structure is used to store both data and instructions. But in separate memory, we have a separate memory for storing data and separate memory for storing instructions. So in unified memory, we have a single memory that stores both data and instructions. So since it is storing both the data and instructions, and we know that both data and instructions are binary streams, a memory can only store ones and zeros. So basically, this data and instruction is stored as binary streams in the memory. So we need some type of control to differentiate which stream is data and which stream is instruction. But that is not the case in this model, where we use separate memory for data and separate memory for instruction. So if we are taking an instruction, then we have to go to the instruction memory. If we want data, then we have to go to the data memory. This model, where we are storing both the instructions and data in a unified memory, this model of a computer is called von Neumann model or von Neumann architecture. So von Neumann architecture is an architecture where we have a unified memory for instruction and data. So for running any program, we have to first store that program and the associated data in the memory. So the first thing that we have to do is to store program and data in memory. And after storing program and data in memory, let's say this is my memory and we have both data and this is the memory. We have both data and instructions stored in this memory. We have to take the instructions and data from this memory. This is called fetching. We have to fetch instructions and data from the memory to the CPU. Then CPU executes those instructions and gives the results. The results are then again stored back into the memory. Okay. So von Neumann architecture is also called stored program computer. Stored program computer. So in this model, let's say, as I said, this is my memory, and in a memory, I have stored some instructions. Instruction is a set of instructions. This set of instructions is called a program. So I have stored program in this memory, and I have also data in this memory. How will my CPU execute this set of instruction? It will get the instructions one by one from this memory. Okay, but getting the data from the memory, the CPU should know the address of the memory location from where it has to fetch the data, because there are millions of locations in the memory. Okay, but CPU has to find out the particular location from where I have to fetch the data or I have to fetch the instruction. So before fetching the instruction from the memory, the CPU should know the address of the location from where it has to get the instruction. Okay, and this address which says us which instruction is to be executed, or the address of the instruction which is to be executed by the CPU, this address is stored in a special temporary memory location that is called program counter. So basically, this program counter, which we called PC, program counter is a spatial memory location, or we say it is a register. It is a register. Register means made of flip-flops. Okay, it is a register inside a CPU that stores the address of instruction that is to be executed. So CPU, before running any program, it will first go to the program counter. Program counter is located inside the CPU. It will see the address from the program counter. It will go to that address in memory, and at that address it will take an instruction. It will get the instruction. Okay, and it will execute this instruction. After executing the instruction, it will update the program counter. So the new value in the program counter will be the next instruction, address of next instruction that is to be executed. So program counter is a special register inside a CPU that stores the address of a memory location where is our instruction located. Okay, and this memory model, where we have separate memory for data and instructions, this memory model is called Harvard architecture. Okay, so let's not discuss in great detail this Harvard architecture, because almost all the systems, current systems, they use von Neumann architecture or unified memory. The another thing that has been added to this von Neumann architecture is the registers. So we have a CPU, we have a memory. And before executing any instruction or getting any data, CPU has to fetch instructions and data from the memory. And after fetching the data, it has to execute the instructions. Okay. So what the computer architects thought, that instead of fetching the data from memory, let's fetch the data from memory, but we will keep this data stored in some temporary locations inside the CPU. These temporary locations are inside the CPU. Why we are using these temporary locations? Because most of the data is reused again and again. Instead of fetching the same data from the memory each time, we will keep the data near to the CPU so that if it wants again the same data, it will find it in its temporary locations. So it will improve the performance. These temporary locations are called registers. So every processor has some temporary data locations which we call the registers, and these registers are mostly 16 to 64. 16 to 64 registers are used, and these registers are named. They are given some names. For example, ARM is an ISA, instruction set architecture, and it has 16 registers, and it names its registers as R0, R1, R2, likewise. Similarly, we have x86. This is also an instruction set architecture that is used by Intel. It names its registers as EAX, EBX, and similar. So before performing any instruction, the data is first brought into these registers, and then the instruction is applied on the data that is stored in these registers, and the final results are then put back into the memory. So the data is first loaded from memory to registers. Then we apply the instruction on these registers, the data stored in the registers. The final output is then stored back into the memory. So first we have to load data from the memory, then we store the data back to the memory. But keep this in mind that every instruction executes on most of the time executes on the data that is stored in the registers. Okay, so now the model is we have CPU, we have memory, and we have a register file. So we have a set of registers inside the CPU. And there are two different types of registers. So one is general purpose registers, which are used for general purpose instructions for adding, subtracting, multiplying. And there are some special registers which have some special functionality. For example, you have seen one such register as program counter. This is a special register, and the function of this program counter is to store the address of instruction that is to be executed next. Okay, and likewise we have another register which we called stack pointer. Stack pointer, in every memory we have a stack. So what is a stack? Stack is a data structure in which we enter the data in first in last out order. So we push the data and we pop the data from the stack. And stack pointer, if I have this stack memory, stack pointer stores the location of top of the stack. So if I have to put some data into the stack, I will put at this particular location. Okay, the stack pointer stores the address of top of stack. We have another register, return address register. I will discuss that return address register later in the course. Okay, so this is our complete model. We have a memory, we have a CPU, and inside a CPU we have registers, and most of the instructions apply on these registers. So this was all about the models of computer architectures, how computer architecture works, what is the register model. We will continue the same in the next lecture, while we will discuss some other models of computers. For example, we will discuss the data flow model, control flow model, and we will briefly discuss about the assembly language. So let's meet in the next lecture. Till then, goodbye.